Okay, so I think because I didn't record properly for the audio, let me add some audio for the context for today's recording. So in today's class, we are actually discuss about the substitution method, another method that is one of the alternatives aside from the one that we have discussed before, like separable equations, linear differential equations, and then the exact equations. Okay, so we call this method a substitution method. So how the methods works? So first we need to, let's say we have a differential equations. So suppose we want to transform these differential equations dy dx, let's say function of two variable xy, with some other function. So we are going to introduce new functions, which is the function g, which has a variable x and u. Okay, so we interchange y and u, and then with some sort of transformations, and then we assume the y function of x, also the g or u is also a function of x. So u is also a function of x. Okay. And then we can rewrite the dy dx and then interchange this f with g, and then we take the product rule of this g, take partial, so take the with respect to x and with respect to u. So we have these two components in this differential equation. Okay, so we have this sort of product forms. And then if we try to solve this, if we try to simplify it and then solve the differential equations, then we could get these solutions, which are going to be defined by this du dx as a function of x and u. And then if we are going to determine the solution, then the solution will be in terms of this u, okay, with, let's say, we have a function of the variable x. Okay, so we have the u, okay, and then at the end we need to revert back to the original equations based on the substitution. So the solution will be equal to y equal, let's say, the function of g, and then x, and then psi of x. Okay. So to make this happen, to use these substitutions, the first thing that we need or we required is the homogeneous property. So if we have a function, let's say we have the functions that has a property f dx dy. D is a multiplication constant that we could, let's say, factor out this d, and then it will be multiplied with the functions. Then we say that the alpha, so for some real number alpha, the function is, we say, homogeneous. function for some degree alpha. Like, for example, okay, if we have this x cubed plus y cubed function, okay, so first we can substitute the x and y with the tx and ty, okay, and we could see that we can write this as a homogeneous function, because we know that this will be a degree of 3, because we can factorize t cubed from the tx ty if we substitute. So we can substitute like this. It's become tx cubed plus ty cubed, right? And then we can say that, okay, we can factorize the t cubed, which means that it is a degree of 3. Okay, so it's homogeneous functions. And then we can try to look on our differential equation form, similar to what we have in the exact equations. So we have this m dx and n dy equal to 0. So if we could figure out the m and n, and we say that this exact equation form, or this differential equation form, it will be homogeneous if the coefficients on both m and n, they are the same degree. Okay. Okay, so we can write the m as a dx dy, and then we can some sort of factor out the t with some power of alpha. And then also for n, we can also substitute dx dy inside, and then we could see that they have the same alpha, which means they are the homogeneous of the same degree. Okay. So if m and n, they are homogeneous of the same degree, then we can also write the x with power of alpha. We can factor out, and then we introduce another variable u, which we can have to make a new functions. So we can let the u equal to y over x, okay? And then we can also make the same condition for n, and we can factor out this x with power of alpha, and then we have a new variable u inside this n. can also do similar things with the x over y. Let's say we have a v to substitute, and then we can also apply to our m and n. Okay. So if we apply those substitutions within this form, we apply this u equal y over x. So the idea is we are going to take this y equal ux, okay, and then try to derive this using the product rule. And then after that, we are going to substitute inside the differential equation forms, and then we can see that all the y will change into ux, okay, and then dy will change in according to the product rule on the specific substitutions, okay. So we are going to substitute all these forms inside this for the differential equations. Okay, so all the results, okay. So we can have, we are having now, it seems like a new differential equation forms, which are having u as our new variable. And then we could simplify this. And by the end of the day, we can try to solve this new differential equation with our familiar methods. Okay? It can be separable, even maybe linear, but mostly we can solve this by separable equations. Okay? So we have this dx over x plus n 1u du divided by m plus un, and then this is equal to 0, which is this is separable, right? So for example, let's say we have these differential equations, and let's just write this. So we have the m and n. Okay, we can identify it easily, and then after that, we can see that both of them are a homogeneous degree of 2, right? Okay, so we can proceed with the substitutions method. Okay, so we could take the, let's say, the y over x equal u as our substitution. So we can write y equal ux, and then we can take the differentials, and then later we can substitute to our forms, the dy, okay? Okay, now we can substitute all the components. So we can substitute y equal ux and also dy. Okay, so we can substitute inside, right? So now we can simplify, and later, after we solve this algebra, we can group all the dx and du, and then see whether we can separate the equations or not, okay? And then we can write this as a dx and du. So we group all the components all together, and I think we can factor out and then make it more simple. So we can have I think separable differential equation method. And we can divide all components, right? And then we try to simplify it and then try to solve this. So dx over x plus 1 over u over 1 plus u du. So we can see clearly that already that this is I think we can try to separate this dx du and then integrate both sides, and that is the separable equations. Okay, so we may need some practical techniques from calculus 1. Especially for this one, we need to get the we rewrite the long divisions form or the partial fractions. Okay, so we have this as a result from our long division, so we can rewrite this and we can exchange these fractions, okay, and then we write with these new forms, which easily can be observed that we can integrate both sides now easily, right? So we could take this and then taking the original equations, which based on our substitution before. So we put back the y over x inside the u, then that will be our actually our proposed solutions. Then we can simplify it and then finding whether we can make it into implicit solution or finding the explicit solution directly. Okay, so both are okay. So after solving the logarithmic parts, and then we can make it into exponential forms, and I believe this will be more clear after we get the exponential forms, and we can have now our proposed solutions. You can simplify this one, and I think will be more, I believe, more simpler forms. So we can write x plus y squared equal the e with power of y over x and then a constant. Okay, later you will see that we can substitute with many ways. Like for example, if we have like cosine y over x squared, then we could say that we can try to substitute with that component as well, okay, to make it easier to solve. Okay, another notes for today's class is about the reduction to separation of variables. So this is additional notes for the substitutions method. So whenever you see a functions that you can identify inside the function, you can see the form of ax plus by plus c. Okay. Then we can also substitute the ax plus by plus c as a u or any v or any variables. Okay. And then to simplify the solution. So let's work on the example. Like for example, this part here, we can see that we have negative 2x plus y inside a squared, which we can try to imagine that that will be our u. Then we can directly substitute. Okay. So let's substitute this part, okay, with u. And then we can have the du dx equal negative 2 plus dy dx. Okay. And later we can try to work out this linear differentials, and then we can substitute the dy dx with this du dx. Okay. Oh yeah, this is should be negative 7. So we have du dx u squared minus 9, which we can also try to separate du and dx into two separate ways. So this can be solved by separable equations, I think, and you will need some partial fractions method, like from calculus 1 to separate the components on these fractions, and then we can integrate nicely each component. Okay, so yeah, please review the partial fraction if you haven't really got into calculus 1 before, so please review that. And I think this will be the end of the recording. And then it's yeah, I'm sorry the recording is not that well, so I need to make a new recording actually, this one. Okay, so yeah, see you next time.